You type a question into an artificial intelligence chatbot and receive an answer seconds later. The exchange feels weightless, almost magical. But your words have entered a physical system filled with processors, cables, cooling equipment, power lines, and machines producing heat every moment they operate. Somewhere, electricity is converted into computation so the model can predict each part of its response. More electricity moves heat away from the chips. Depending on the facility, water may help with cooling or may be consumed indirectly by the power plants supplying the grid. That does not mean one innocent question is destroying the planet. Simple text prompts can be surprisingly efficient. The real story is more complicated. Different questions can have radically different footprints, and tiny individual costs become significant only when multiplied across enormous systems and billions of interactions. So what actually happens after you press send? How much energy can an answer require? Why do some data centers need water while others avoid it? And when companies promise more efficient AI, can total consumption still rise? To answer, we must follow the question into the machine. Your prompt first travels through ordinary internet infrastructure, a router, local network equipment, fiber links, and facilities operated by service providers. It is directed toward computing capacity where the requested model is available. The distance may be invisible to you, but the journey is entirely physical. Inside the data center, servers contain specialized processors designed to perform huge numbers of mathematical operations in parallel. The model does not search a hidden book containing your answer. It repeatedly calculates which token should come next, using patterns encoded during training and the context you supplied. The processor is only one part of the work. Data must move between accelerator memory, ordinary memory, central processors, storage, and networking equipment. Capacity must also remain ready for sudden traffic. Machines waiting for the next request can still consume electricity, even when they are not producing visible answers. Almost all the electricity entering this equipment eventually becomes heat. Fans, pumps, heat exchangers, chillers, or cooling towers must carry that heat away. Without them, temperatures would rise, processors would slow down, and equipment could shut itself off to prevent damage. Computation and cooling are inseparable. Before a chatbot can answer anyone, a model must be trained. During training, large clusters process examples repeatedly and adjust billions of internal values. This can occupy powerful hardware for extended periods. Training creates the capability, but it is not repeated from the beginning whenever you ask a question. Your question belongs to a different stage called inference. Inference means running an already trained model to generate a prediction or response. One inference may be small compared with a major training run, but popular systems perform inference continuously for vast numbers of users, turning repetition into scale. The workload also changes with the request. A short factual answer requires less computation than a long reasoning process. Creating a high-resolution image is different from generating text. Video generation, complex agentic tasks, and repeated tool use can require hundreds or thousands of times more energy than simple text generation. This is why the phrase "an AI question" can be misleading. Asking for one sentence, analyzing a long document, generating several images, and creating a video are not equivalent actions. They may use different models, different hardware, different amounts of time, and dramatically different quantities of computation. Online claims often assign one dramatic amount of electricity or water to every AI prompt, but there is no universal number. The model answer length, chip generation, server utilization, cooling design, local climate, and power grid can all change the result. Even the measurement boundary matters. In 2025, Google estimated that the median text prompt in its Gemini apps used 0.24 watt-hours of electricity and 0.26 milliliters of water. That was roughly 5 drops of water, far below many viral estimates circulating online at the time. Yet this result describes one company's text product, infrastructure, methodology, and measurement period. It cannot automatically describe another model or a request for video, images, deep reasoning, or autonomous actions. A transparent case study is useful precisely because it reveals how specific every estimate must be. Water estimates are even more location-dependent. Berkeley lab researchers found that workload-level water use can vary by more than 10,000 times. Server efficiency, cooling technology, climate utilization, and the water used to generate electricity can all transform the footprint of the same digital task. A tiny cost does not remain tiny when a service becomes global. Data centers consumed about 415 terawatt-hours of electricity in 2024, according to the International Energy Agency. That was around 1.5% of all electricity used worldwide during the year. Artificial intelligence was only part of that total. Data centers also run cloud software, streaming, online stores, financial systems, storage, and ordinary websites. But AI is now a major source of new demand, because specialized servers are spreading rapidly and increasingly intensive applications are reaching more users. The IEA reported that global data center electricity demand grew 17% during 2025. Consumption from AI-focused centers grew even faster, rising 50% in that year. Its updated central projection sees total data center demand roughly doubling from 2025 to around 950 terawatt-hours in 2030. Forecasts are not destiny. Adoption could slow, hardware may become more efficient, projects may face grid delays, and new applications may consume more than expected. The important point is not one perfect prediction. It is that electricity planning must now account for digital infrastructure growing at industrial scale. A hyperscale AI data center can demand 100 megawatts or more. The IEA compares that annual electricity use with approximately 100,000 households. Some of the largest facilities under construction are designed for 20 times that power, approaching the scale of major industrial complexes. Unlike a factory that can be distributed across many towns, data center capacity often clusters in a few locations. That concentration can place sudden pressure on substations, transformers, transmission lines, and power generation plants. Global percentages may appear modest, while the impact on one local grid becomes extremely significant. Building the computers is also a physical industry. Accelerators require semiconductor fabrication, advanced packaging, memory, circuit boards, metals, and complex global supply chains. Server generations are replaced as newer hardware performs more calculations per watt. The cloud may sound immaterial, but it begins in mines, factories, and cargo routes. Then comes construction: land, concrete, steel, backup generators, cooling systems, electrical switchgear, and miles of cable. The answer appearing on your screen is the final visible moment in a process supported by infrastructure that may take years to permit, finance, manufacture, connect, and build. Water enters the story because computation creates heat. Some facilities use evaporative systems, where water helps remove heat efficiently, but part of it is consumed through evaporation. Others rely more heavily on air cooling or closed liquid loops. Every design balances energy, water, climate, cost, and reliability. Direct consumption at the facility is only one layer. Producing electricity can also consume water, depending on the power source and cooling technology used by the generating plant. A data center with little water use on site may therefore retain an indirect water footprint through the grid supplying its electricity. Location changes the meaning of every liter. Consuming water in a cool, water-abundant region is not equivalent to consuming it during drought in a stressed watershed. Responsible comparisons must ask where the facility operates, what kind of water it uses, and what competing needs exist nearby. New designs can reduce the trade-off. Some operators are developing direct-to-chip cooling and systems that avoid evaporating water during normal operation. Better cooling, heat reuse, efficient hardware, and careful siting can lower impact. But improvements must be measured transparently rather than accepted as marketing language. Two identical prompts can produce different emissions when the machines use different electricity. A server supplied by low-carbon power is not equivalent to one operating on a fossil-heavy grid. Time can matter too, because the mixture of generators supplying a region changes throughout the day. In 2024, the electricity physically supplying data centers worldwide came from a mixture dominated by coal, renewables, natural gas, and nuclear power. The proportions differed sharply between regions. A corporate renewable contract also does not necessarily describe the exact generators serving a facility at every hour. The IEA expects renewable generation to meet nearly half of the growth in data center demand through 2030. Yet natural gas and coal are also expected to provide a substantial share of the additional electricity in the near term. Growth can therefore support clean energy investment while also extending fossil generation. AI can also help the energy system itself. Researchers use it for weather forecasting, grid optimization, equipment monitoring, and discovering new materials. These benefits could reduce costs and emissions elsewhere, but a potential benefit does not erase the infrastructure required to deliver it. Both sides belong in the calculation. The encouraging fact is that AI tasks are becoming more efficient extremely quickly. The IEA says energy use per task has recently fallen by at least an order of magnitude each year. Better chips, smaller specialized models, quantization, improved software, and higher utilization can produce more answers from each unit of electricity. Efficiency does not automatically reduce total consumption. When a service becomes cheaper, faster, and more capable, people may use it more often and invent heavier applications. Video generation, constant reasoning, and autonomous agents can absorb savings created by efficient text models. The final outcome depends on efficiency multiplied by demand. The solution is not to feel guilty about every useful question. It is to demand meaningful disclosure, efficient models, cleaner electricity, responsible locations, better cooling, and applications valuable enough to justify their resources. Users, companies, utilities, and governments influence different parts of that system. An AI answer may appear from nowhere, but nowhere has a location, a power connection, a cooling system, and a supply chain. The real question is not whether one prompt has a hidden cost. It is what we choose to build when billions of those costs become one physical machine.